Welcome back to Neural Intel. Today we're diving deep into a fascinating new approach in neural network training called NoProp. You shared some compelling research on this, and we're going to unpack exactly how it works and what makes it so different.
Yeah, it's definitely a shift in perspective.
Think of backpropagation, the workhorse of deep learning, like the super organized chain of calculations. Errors go backward, tuning the network.
Right, the standard forward pass, then the backward pass for gradients.
But that chain, it can get really long and heavy, especially with these massive models we see now. It leads to memory bottlenecks, makes parallel processing tricky.
Exactly. The research you sent points out those limitations. Biological plausibility is a big one, but also just the sheer memory demands from storing all those intermediate activations for the backward pass.
And that sequential nature of the backward pass really limits parallel computation, doesn't it? Plus, issues like catastrophic forgetting can crop up.
They certainly can. Holding on to all that state is costly. And yeah, the brain definitely doesn't seem to work quite like that, which is why people are looking for alternatives.
So this is where NoProp comes in as, well, a completely different ballgame. The core idea.
Yeah.
It just sidesteps traditional forward and backward propagation.
Completely. It's drawing inspiration from diffusion models, how they generate data, and also flow
Mostly.
matching techniques.
And the really intriguing part, for me at least, is that each layer learns independently. It's like each one is just trying to clean up a noisy version of the final target.
That independent learning is key. Instead of that synchronized forward-backward dance, it's more modular. Each layer focuses on its own local task, mapping its input towards the target without needing direct gradient info from later layers.
Okay, so our mission today. Get into the technical nuts and bolts. How does this denoising work layer by layer? How's the network structured for this? And crucially, what are the early results looking like on benchmarks like MNIST, CIFAR 10, CIFAR 100, especially compared to backprop and other backprop-free methods?
Right, let's see how it stacks up.
Prepare for some aha moments, hopefully, as we explore this fundamentally different training method. So let's start by getting a solid grip on the core idea. What is NoProp, fundamentally?
At its heart, NoProp wants to train deep networks without that classic forward or backward signal propagation. It borrows heavily from diffusion models, where the main goal is learning to reverse a noise-adding process. Like reconstructing a clear image from a blurry one.
And the key differentiator is that each layer does this denoising independently. No chain reaction of gradients.
Precisely. That independence is the major departure. Now, to make this work, NoProp does something a bit unusual. It requires fixing the target representation at each layer beforehand, and it fixes it to be a deliberately noisy version of the final target, like the class label.
Whoa, okay, so if we're classifying images, the intermediate layers aren't necessarily learning edges, then textures, then object parts, like in a standard CNN.
That's a really important point the authors make. NoProp might not be learning hierarchical representations in that familiar way. The intermediate states aren't really abstracting features from the input image. They're being directly nudged towards a noisy version of the label itself.
Okay, that's a fundamental shift. Let's get into the mechanics.
Yeah.
How does the discrete-time version NoProp DT actually work?
Right, NoProp DT. It introduces this sequence of stochastic intermediate activations. Let's call them Z111, all the way up to 8010. Think of them as snapshots as data gets progressively noised or, in reverse, denoised over two ballers.
And this process is defined by the forward process, beta.
Correct. The forward process T defines how you get from one step to the next. ZLODS is calculated from the previous state ZLONL and the original input $6. The equation looks a bit like a residual connection, actually. ZLOD says D to C plus BT ZBON plus squirt epsilon.
So you keep some of the previous state, add a transform component, and some Gaussian noise, epsilon. And importantly, that transformation how depends on the original input, $6 at every step dollar.
Yes, that's a key detail. The input $6 conditions that transformation at each discrete time step. It's not just used at the very beginning.
Okay. Now, what about the other piece, this variational posterior? What's its job?
The variational posterior dollars is like the learning guide. It approximates the ideal reverse process, how you'd ideally get from the noisy state back towards the clean label. NoProp-ET uses a specific stochastic process, a variance-preserving Ornstein-Uhlenbeck process, to define the relationships between Zillites-Wieland and the labeled dollar.
And the paper shows that using this process, you can define QZ1 and Qs near as nice, manageable Gaussian distributions.
Exactly. And from those, you can derive Qzl and Qs and UN also as Gaussians with specific means and variances. Those are laid out in equation 6.
And these Gaussian forms are crucial because they let you write down the overall NoProp objective function, little NoProp, in equation 8. That's what the network actually minimizes.
Precisely. That objective function brings it all together. It has a few main parts.
Okay, let's break that down. One part looks like it's about predicting the final label gal from the final noisy state, $0.
Yes, the first term is basically the expected negative log likelihood of predicting the correct label, giving that final state $0. There's a classifier, that output, that takes $0 and outputs label probabilities.
Then there's a KL divergence term comparing QLEO with some prior P.
All right, the LAO-LAPZ, that encourages the initial noisy states, conditioned on the label, to look like a simple prior, usually just standard Gaussian noise. It keeps things well behaved at the start.
And the final piece, the one averaged over time steps, compares the learned transformation tele and CAX with the label embedding JH. This was like where the independent learning happens.
That's exactly it. This term, SNRT-ADEN XNO2, is the core of the independent training. For each time step 10EO, the block gets trained, using a simple L2 loss, to directly predict the embedding EO of the correct label.
Using as inputs 0T and the original image $6.
Right. And crucially, this training happens for each SNN independently. There's no gradient flowing from T plus $1 back to $2. Each layer or time step block is just trying to map its specific inputs directly towards the target label embedding.
So basically, each layer takes a noisy version of label plus the image info and learns to denoise it a bit, pushing it closer to a cleaner representation of that label.
That's a really good way to put it. Each block learns a localized, image-conditioned denoising function aimed squarely at the label embedding.
Which is so different from learning intermediate features like edges or textures. Okay, now the paper talks about variations. What about fixed versus learnable label embeddings?
Yeah, that's an important choice. You can either fix star-fo and deal beforehand, maybe use one-hot vectors, so it's just the identity matrix, or you can make one.or part of the trainable parameters.
Does learning the embeddings help?
It seems to, especially in some cases. The paper notes that when you learn the embeddings and make their dimension match the input image dimension, they can start to look like learned image prototypes for each class, which is pretty cool.
Interesting. And what about going continuous? NoProp CT?
Right, NoProp CT takes the limit as the number of discrete steps $t goes to infinity. This leads to a continuous time formulation, like a differential equation. You get a new objective function, equation 9, involving a single learned block xt that now also takes the continuous time as input.
So one block handles the dynamics across all noise levels instead of separate blocks for each discrete step.
Exactly. It's very much related to neural ODEs, but the training is different. Standard neural ODEs often need backprop through the ODE solver or use the adjoint method. NoProp CT avoids that by learning the dynamics that reverse a predefined continuous noising process, sampling points in time independently for training.
That sounds potentially more efficient. Then there's another continuous version. Flow matching. NoProp FM. How's that different?
Flow matching is an alternative continuous formulation. Instead of explicitly reversing a noise process, it tries to directly learn a vector field, VFCCTTX. This vector field defines an ODE that smoothly transports samples from an initial noise distribution to the distribution of the target label embeddings UU.
How do you learn that vector field?
Well, the ideal field is unknown, so you learn a conditional field 5FCZEEC, where Z those the initial noise and $Z is the target embedding UU. A simple choice is just the vector field corresponding to a straight line path between $Z and Z. The objective, equation 11, then trains a network viver to match this target vector field.
Makes sense. And they mentioned an anchor loss for flow matching when embeddings are learned.
Yes, that's important. If you learn the embeddings at the same time, they could all just collapse to the same point. So they add a standard cross-entropy loss, equation 13, calculated on the predicted class probabilities to keep the embeddings for different classes separated and meaningful.
Right. Prevents degenerate solutions. Okay, let's switch to implementation. Figure 1 shows the inference process. How does prediction work once the model is trained?
For inference, you start with a random Gaussian noise, $Z. Then you pass it sequentially through the trained blocks, CSM. Each block takes the previous output, z sys sum, and the original image, 6 sum, and computes ZIL dollars. After taps, you get the final state c sys sum. A simple linear layer plus a softmax function is then applied to ZL sum to get the final class probabilities.
So even though they're trained independently, for prediction, they form a sequence.
Exactly. Training is independent, but inference is sequential. For flow matching, it's similar the learned publets approximate the OD steps. The final prediction ADDIE is often made by finding which learned class embedding is closest, like Euclidean distance, to the final state dollars.
And figure 6 in the appendix details the architecture for those stop blocks.
Yeah, for NoProp DT, the block HAL takes the image $6 and the noisy label $. The image goes through some conv layers, then a dense layer. The noisy label $LA goes through its own dense network, maybe with batch norm and ReLU. These two pathways get concatenated and fed into more dense layers.
And the output.
The final layers produce logits. These logits go through a softmax to create weights. The actual output Hathers is then a weighted sum of the class embeddings in Lalais using those softmax weights.
How about for the continuous versions, CT and FM?
Yeah.
Any changes?
Mostly similar, but they add the continuous timers in input. Usually, TIL is encoded using positional embeddings, processed and then concatenated with the embeddings of $6 in the current state, Z dollars. A key difference for flow matching's output, VIO, is that it outputs logits, which are used directly as weights for summing class embeddings, no softmax there, allowing more flexibility. And for the final prediction layer, in all versions, it's typically just that linear layer followed by softmax on ZD dollars.
Got it. The paper also mentions noise schedules. Fixed cosine for DT, but trainable for CT.
Yeah, the fixed cosine schedule for DT is a standard, decent choice. For CT, making it trainable lets the model potentially find a better way to remove noise for the task. They parameterize the signal-to-noise ratio, SNR, using a small neural network ensuring it's monotonic, and that determines the noise level at time 2.
Okay, fascinating details. Let's get to the results. Table 1, classification accuracy. How does NoProp DT perform?
The results for NoProp DT look really strong. The paper shows it achieves accuracy comparable to, sometimes even better than, standard backprop-trained CNNs on MNIST, CIFAR 10, and CIFAR 100.
Better than backprop. Wow.
Or at least highly competitive. And, importantly, it significantly outperforms other backprop-free methods they compared against, like forward-forward and difference target propagation.
That's very encouraging for a completely different paradigm. What about the continuous versions, CT and FM?
Generally, NoProp CT and FM showed slightly lower accuracy than DT on these tasks. However, they often did better than the adjoint sensitivity method, which is a common way to train things like neural ODs. Figure 3 shows CT can be competitive with adjoint in accuracy and often faster, especially on MNIST and CIFAR 10.
Interesting trade-offs.
Yeah, and there was that interesting point about NoProp FM on CIFAR 100. It struggled a bit with fixed one-hot embeddings, but improved quite a bit when the embeddings were learned.
Right, highlighting that embedding choice again. What about memory efficiency and Table 2?
That's a clear win for NoProp. Table 2 shows both discrete and continuous versions use significantly less GPU memory during training compared to backprop and the adjoint method. That's a big practical advantage for large models or limited hardware.
Definitely a plus. And Figure 2, visualizing the learned embeddings as image prototypes.
Yeah, for CIFAR 10, when the embedding dimension matched the image size, they initialized with sort of average images per class. After training NoProp DT, these embeddings evolved into much clearer, more representative visual prototypes for each digit or object class. It suggests it's learning meaningful class representations, even if not hierarchical features.
Interesting. And the ablation studies in Figures 4 and 5. Figure 4 looked at the final prediction layer, softmax versus posterior probability.
The takeaway there seemed to be no clear winner. Sometimes softmax was slightly better, sometimes the posterior approach, depending on the data set. No consistent advantage.
And Figure 5 on initializing the embedding matrix, MemEmbed, random versus orthogonal versus prototypes.
That showed that using either orthogonal initialization or the prototype image initialization generally worked as well as, or often better than, just random initialization. So a good starting point for the embeddings seems helpful.
Okay, solid results, clear memory benefits. Now let's circle back to that representation learning perspective the authors bring up. They argue NoProp isn't really doing representation learning in the traditional sense.
Right. Their argument is that because the intermediate states are explicitly constructed as noisy versions of the target label, or interpolations towards it in FM, the network isn't learning to extract abstract features from the input data in a hierarchical way. The representation at each layer is defined by its relationship to the label, not necessarily by abstracting patterns from the image pixels upwards.
Which leads him to ask that really provocative question. Is traditional hierarchical representation learning actually necessary for deep learning to work well? NoProp's performance suggests maybe not always.
Exactly. It challenges that core assumption. If you can get strong performance by carefully designing the information flow and the nature of intermediate signals, even if they're tied directly to the label, maybe deep learning doesn't have to rely on learning abstract future hierarchies.
And they note that these intermediate signals in NoProp don't necessarily get more abstract layer by layer, unlike standard deep nets. It really makes you rethink the role of those hierarchies.
It absolutely does. It opens up avenues for designing architectures with different inductive biases, perhaps better suited for certain tasks or constraints, especially considering backprop's own limitations like differentiability requirements and sequential dependencies. Maybe we can design the intermediate information flow more directly.
Okay, let's try to wrap this up and think about what this means for you, our listener.
Yeah.
We've gone deep into NoProp, a really novel method that completely breaks from the backprop mold. Getting competitive results without forward or backward passes, that's pretty remarkable.
And the really mind-bending part is this challenge to hierarchical representation learning. Fixing intermediate states as noisy labels and still succeeding, that shakes up some fundamental deep learning assumptions and opens doors for totally new ideas.
Think about the implications. Could this lead to more biologically plausible algorithms? The independent layer training, could that unlock more efficient distributed learning? And that lower memory footprint is a huge practical win, as the research showed.
It really makes you wonder, if changing the information flow so drastically can work this well, what else is possible? Could we tailor these intermediate representations layer by layer for specific tasks even more effectively?
NoProp is a big step into exploring that new territory. It proved there are viable alternatives to backprop, alternatives that might be better in terms of efficiency, maybe even accuracy compared to other non-backprop methods. It definitely gives us a lot to chew on regarding how necessary traditional representation learning really is.
We definitely encourage you to check out the paper links in the show notes to see all the math and experimental details. This field moves fast, and understanding these fundamental shifts is key. What part of this no-prop idea stands out most to you? We'd love to hear your thoughts. Thanks for joining us for this deep dive on neural intel.